Welcome to the Allen School Colloquium. It's a pleasure to have Anurag Anshu here joining us from Berkeley. Uh, Anurag did his PhD at the Center for Quantum Technology at NUS in Singapore. Then he was at the Perimeter Institute in Waterloo before going to where he is now to do a postdoc in Berkeley. He's going to tell us about computational phenomena in quantum constraint satisfaction, which is, of course, the subject of the far less well-known Rolling Stones song, I Can't Get No Large Projection Onto the Satisfaction Subspace. That's a joke. Over Zoom, you don't have to be able to read a room. So without further ado, Anurag, glad to have you.
Thanks a lot, James. Thanks for the intro and the joke. And it's great to talk to you, all of you, about this. So let me start the talk with the most familiar term in this title. It's not and, it's constraint satisfaction, I believe. So let's get started on that. So constraint satisfaction is ubiquitous in nature, and we see it coming up in puzzles, coming up in networks, in scheduling problems, and so on. What's exciting about these problems is that they also come up in different areas of natural science, like physics, biology, economics, and so on. In particular, we see the role of NP completeness as kind of putting limits on various natural problems in these disciplines. So constant satisfaction and whatever has happened after that, it has really shown the power of the computational view on nature. That indeed this is a very important view to take when studying natural sciences. And a very important outcome of the computational view on nature is quantum computing, which was independently proposed in the early 80s by Benioff, Manin, and Feynman. And the idea here was to use the subatomic particles to perform computation, which led to the current field of quantum computation. So my research in quantum computing is in an area known as quantum complexity, and particularly focused on the quantum version of these constraint satisfaction problems. Moreover, this research has implications in natural sciences, and in particular in an area known as many-body physics. So in this talk, I'll be describing all this, and to be more specific, just to tell you what you expect to see in this talk, there'll be a series of developments that I will tell you on answering questions on quantum constraint satisfaction problems, which, by the way, I'll be calling it as quantum CSP right now, and with application to many-body physics. So let me just quickly go through that. I will talk about a learning problem in this area, which is in fact motivated by quantum machine learning, and in fact a very natural problem for probing interactions in nature. I'll talk about this. I'll talk about solutions to these quantum CSPs, and in particular solutions which are physically relevant, which you see in day-to-day systems. And here we'll also see that an information theoretic aspect enters in the discussion, which I'll talk about. Finally, for those who like hardness of approximation, I'll also discuss the hardness of approximation for these problems. In particular, I'll talk about a quantum PCP conjecture. And here we'll see some structural discussion. We'll see the appearance of quantum circuits. So overall, what the take-home message from this whole talk will be the following, which is that computational ideas, which I will talk about, in particular, I'll talk about polynomial methods and strong convexity and so on, but that's fine. What's important is that the computational ideas, they reveal surprising properties of these quantum CSPs, and that has applications in many-body physics. And what's more important than these developments it was not possible to capture them with the prior methods. Along the way, we will see implications for quantum computing everywhere. And why is that? It's very simple. It turns out that a quantum computer is simply a quantum many-body system that is performing computation. So we'll see how all the discussions will have implications for quantum computing as well. So one thing to note, one thing to probably note in the talk would be that the quantum view on natural sciences seems, in particular in physics, seems to have impact not just in the computational aspect, but also in other aspects, like the structure and information theory and so on. which is unlike what happened with the classical constant size function, which mostly had impact in the computation aspect. All right. So in fact, there's a part of my work which I will not be discussing. So for that, I'm going to take a short detour into a different track for this slide only. And this part of my work, it connects to quantum communication complexity. And in particular, this discussion is about certain methods to understand quantum communication complexity. One method is known as quantum information complexity. And in this work, this work was inspired by the research that was done here. I mean, at University of Washington by Anup Rao and Makarand Sinha. And similarly, another part of my work, it connects to another way of understanding quantum communication complexity known as log approx rank, which also incidentally was involved Makarand Sinha as someone who did this work independently. Furthermore, in the same quantum communication, there was this result on, I had some work in quantum rejection sampling, which was inspired by these methods in the classical computer science in communication complexity, where once again, two of the most important works in this area also involved Anup as a co-author. So, I mean, all these results, I will not be able to talk about due to time constraint, but what's important is that this line of work also turned out to have implications in physics and quantum channel theory, which brings us back to our track of this talk, which was essentially that the computational ideas, in particular rejection sampling from communication complexity, found impact in other areas of research. All right, so let's go back to our discussion and let's go to the first part of the talk, which will be about learning problem. So one of the issues with quantum mechanics in general is that quantum states are somewhat unusual. For example, if you look at a quantum state, it can change suddenly. So it can be difficult to kind of get used to it without a lot of background. But what really helps is that there are several classical analogies that one can focus on. In particular, one analogy that will help us in this talk, in fact, for most part of the talk, will be that of graphical models. We'll see a lot of contact with the notion of graphical models. So I will be describing a bit about these objects in this slide. So graphical models are certain probability distributions which are defined by a graph. Well, that's what makes it graphical. And they have some very nice properties. So for example, if you look at these 6 variables, 1 to 6, and if you look at the edges, the graphical model specifies certain correlation between these variables. So for example, in this picture, the distribution on these 6 variables factorizes into this form, which involves these variables as a distribution over them, and condition on them, there's a distribution on other variables. So the whole point of graphical model is that it helps to simplify the complexities of a probability distribution by breaking them into small parts. And this breaking up is determined by the graphical structure of the graph. So there's a famous result in statistics, which in fact tells us how these graphical models look like. And there is a specific distribution associated to these objects. So again, looking at the same graph, let's say there are some values to these vertices, x1 to x6. Then it is known that under most conditions, the distribution of the graphical model looks like this. It's an exponential of certain object, and it's a sum over all the edges of this graph with some weight, that's a, let's say a12 is the weight of vertex 12, times these x1 and x2 and so on. So this distribution is something that comes along with graphical model bona fide, but it requires a proof though. So given the graphical models, which are in fact very, very useful and important in statistic, there is a very interesting family of problem that comes up. And the problem is as follows. If I'm given samples from this unknown graphical model, that means I'm given lots and lots of such distributions, is it possible for me to infer this underlying graph, which may not be known, or to figure out these edges, edge strength A12 and A13 and so on? So this problem is one of the central problems in machine learning, and it has seen a lot of development in the past decades. I'm just referring to some of the many important works in the theory side, but several results have studied this particular model. So the importance here is that the graphical models help simplify the nature of correlations that occur in many systems. So to go from these graphical models to a quantum graphical model requires, on the mathematical level, some change of perspective, I guess. So the change is to look at these edges. So let's say I look at AI and one of the edge ij. One replaces that with a matrix H. Let's say Hij or H12. And once we do all of this, we obtain a quantum version of this graphical model, which is also known as Gibbs state in the physics community. So this looks very similar to what I showed you earlier. It's an exponential of sum over all the edges with the weight Hij on this, replacing the original Aij. Now, this particular object over here, since Hij is a matrix, this whole thing is also a matrix. This matrix is known as a Hamiltonian, which is a term that comes from the physics community, and I'll be carrying over this term throughout the talk. And it turns out that this will be important in other parts of the talk too. I'll be abbreviating Hamiltonian with H. So just like the classical problem of learning a graphical model, we can also ask the similar quantum version of this problem, which is the quantum graphical model. And it goes as follows. We'll soon see that this problem becomes very relevant in the context of upcoming quantum computing and so on. So let me describe it in the similar context. So imagine a quantum device, certain machine, a black box, which has a hidden Hamiltonian inside, H. And imagine that it gives lots and lots of samples from this quantum graphical model, which depends on the Hamiltonian. The question is, I would like to study these samples, and I would like to infer the Hamiltonian slightly, allowing errors, and I would like to get as close as possible to the original Hamiltonian. So this is precisely the kind of problem that we solve for the classical graphical model. And the question is, how can I minimize the number of samples for a given notion of accuracy for this problem? So this problem on its own, this seems to be this is a quantum version of the classical graphical model problem, but it has seen a wide range of motivations in several contexts. So, for example, one can imagine in the setting of experimental physics, where one discovers a new material or new interaction. How does one understand what's going on inside? So that's where this problem comes up. It's a canonical problem in the field of quantum machine learning, and also in quantum algorithms, where these quantum graphical models or Gibbs states have been showing up very recurrently. In fact, this work was done at the Microsoft research, again near University of Washington. So all these places one sees this problem to be naturally appearing. Now, what is the central challenge of trying to figure this out? This seems to be a pretty important problem, but it seems that the way I'm putting it forward, it seems to be hard to solve, unlike the classical case. So challenge is the following. Just to sum up very quickly, if you have a graphical model, a quantum graphical model, which you're not looking at right now, and if you start looking at any of the edges, it can completely disrupt the information about other edges at other places. This property doesn't really occur in the classical case, but it occurs in the quantum case. So let me quickly get into that. So classical case, what happens is that the learning of the graphical model relies heavily on what is known as a Markov condition, which roughly says that a given edge, it doesn't depend too much on other edges far away in a certain sense. But in the quantum case, for these quantum Gibbs states or quantum graphical models, they really can violate this condition in a major way. So we cannot really appeal to this property. And that is in a moral sense captured by the picture that I showed you in the previous slide. So in fact, there are several heuristic ways to try to solve this problem, but there was no rigorous analysis. There's no proof that this problem can be answered. In a recent work, we showed how to solve this problem in a notion using some procedure which was efficient in terms of the number of samples, which was the sample complexity of the task. And The key technical tool which we used was, I'll just mention it here, I won't describe it. It's known as the strong convexity of what is known as a quantum partition function, which sort of tries to deal with this issue I showed in the previous picture about that one particular interaction can mess up the interactions everywhere else.
Anurag, there's a question in the chat from Shyam about what's the importance of quantum graphical models, and does it have implications for solving machine learning problems?
Right. Thanks. Thanks for the question. Some motivation comes over here. So if you want, particularly in the context of quantum learning, you can think of quantum graphical models as kind of an ansatz for describing the system that operate in nature, for system that operate at low temperatures. In general, quantum graphical models are very important in physics because they describe the property of physical systems in most cases. Now, this problem on its own is not the only ansatz in quantum machine learning. There are several, and I'll talk about them in one of the coming slides. But it's in the context of quantum machine learning, it's one of the ansatz that people can use to describe something unknown that they want to learn. So does that answer the question? Or
yes, thanks.
So given this, let me tell you again, thanks for this question, because that builds up to my list of open questions in this, my favorite list of open questions in this line of work. And this is a slightly busy slide, so let me explain what's going on here. Quantum graphical models are, or quantum Gibbs state, these are certain types of quantum states. And in practice, there are several quantum states that occur in nature. So for example, you might have a quantum computer that works for a short time, one that works for a pretty long time, for example. And we'll also see a certain class of quantum states later, which are known as tensor networks. So an important question is, just like the quantum graphical models or Gibbs states, one question is, can I really learn these systems efficiently? And there seems to be sort of a curve associated with this, which I just called it learning curve. It's not a standard term at all. And essentially, the picture seems to be that as the quantum states get more complex, in a notion of complexity that I will talk about in the coming slides, but in some notion of complexity, it seems that learning them gets harder. In particular, there are ways to learn these systems pretty efficiently, but there are no ways to learn these systems by far. Our research shows that the Gibbs states are particularly special. They are quite complex, but still they seem to be easy to learn. So the question, so one important open question is it possible to understand whether these class of systems one can learn these systems or not? And in fact, this question seems to be a question of interest from theory point of view for now, but it turns out that it also has a lot of importance in what's happening these days. So these quantum states that I mentioned, short or long quantum computation, this tensor network states and Gibbs states, one expects that these are the quantum states that will be output in a programmable feature quantum device. So one question here is that, is it possible to verify the performance of this device? That is, when given a device, an experimenter designs the device in a certain manner, and the experimenter expects the device to produce to do a short quantum computation of certain type or produce a Gibbs state. Then how do we know that this device is really doing as expected? And this comes to the problem of verifying these quantum states that they are working as expected. So this problem can of course be solved if you have a good way to learn these quantum states. But another very interesting question is, very important question is to figure out whether there are easier ways to do so. And in particular, is it possible to verify all these quantum computations? All right, so that brings me to the end of the first part of the talk. There was already a question. If not, then I'll move to the second part, where we'll go into more details of quantum constraint satisfaction problems. In this part of the talk, we'll talk about several concepts. We'll talk about complexity that I quickly touched upon in one of the previous slides, and we'll talk about the phenomenon of entanglement. All right. So let's talk about about the constraint satisfaction problems in a more abstract manner. So they occur everywhere, but there is a way to kind of distill the structure in a simple way. And here's one way, which is we can think of the variables in the CSP as these blue objects. They are just certain variables. They take values 0 or 1, each of them. And there are a collection of constraints on these variables. So for example, there's a constraint over here and so on and so forth. One example of a constraint is a constraint, let's say, between these two variables. It could say that I would like the AND of these two variables to be 1. So that's a kind of constraint. We put together all these constraints and we get a quantum constraint satisfaction. Sorry, we get a constraint satisfaction problem. To go from here to the quantum CSP is the same rule that I showed you earlier when it came to the graphical model, which is slightly surprising, but it does work that way. So what we do is that we take the constraint. We first we take the variables as before. We turn them into the quantum units of information, which is a qubit, which mathematically is seen as a two-dimensional complex vector space. That's fine. So we do that, and each of the constraints get replaced by a matrix, which, if you recall, I have been calling it as a Hamiltonian. So same rule applies here. And once we get this, we can talk about the dictionary between the classical constraint and the quantum constraints. So as I mentioned, all the variables get replaced by qubits, which are each of these particles, and each constraint get replaced by a quantum constraint, which is a Hamiltonian. Now, when I take all these constraints together, I get back the same thing that I discussed earlier, which is known as the Hamiltonian, which is the sum over all these quantum constraints. So you might be wondering that why. So first of all, I talked about this arriving at the Hamiltonian from the point of view of classical graphical models, and I'm talking about arriving at the Hamiltonians from the point of view of constraint satisfaction problems. The fact that they are the same objects seems somewhat surprising, but this also helps us a lot because we can continue the analogy with graphical models, and we'll see how it shows up later. So anyway, so this is my quantum constraint problem. It's a Hamiltonian, and let's see what more is involved here. So far this completes the mathematical description of these objects, but the next thing to consider is the assignment. So in the case of CSPs, an assignment is a value to each of the string. It goes from it's an n-bit string if there are n particles here. In the quantum case, an assignment turns out to be a quantum state, which happens to be a vector in this joint vector space of all these particles. So as I mentioned earlier, that each particle, each qubit, or each quantum variable is a two-dimensional vector space. So if I combine them together, the rules say that they become jointly a 2 to the power n dimensional vector space, and that gives a quantum state as an assignment. And the solution to a CSP, which would be one of any of the strings or assignments which minimize the number of violated constraints, they're replaced by what is known, again, this term comes from the physics community, it is known as a ground state, which is a quantum solution to these quantum CSPs. Now, there's another quantity of interest, which we'll keep track of, and that is the amount of unsatisfaction you see for a given quantum constraint satisfaction problem. So given a quantum CSP, we are trying to minimize the number of constraints that are not satisfied. So we'll be accounting for unsatisfied fraction value of a given instance for a given quantum assignment. All right, and it turns out it's also known as energy density in the physics community. So just like constraint satisfaction problems are very, very important in computer science, quantum CSPs are also very, very important in other real world settings. So for example, in the study of very low temperature physics, they turn out to play a very important role. In quantum computation, the solutions to quantum CSP are very important ways to model quantum computation, which I will not be getting into the details of. So given this dictionary between classical and quantum CSPs, let's talk a bit more about these solutions. So a solution to a classical CSP is a string. It's a bit string, and we know from the theory of NP hardness that it can be hard to find. In a very similar manner, the solution to a quantum CSP can also be hard to find. Well, simply because the quantum CSP is a generalization of a classical CSP. But there is an additional layer of complexity that comes when it comes in the context of quantum CSP, and that is that these solutions can also be hard to describe. So in the case of classical CSPs, the solution to describe this solution, you just have to tell the string. And string is very easy to describe. It describes itself. But for the quantum case, that doesn't happen. And it's possible that in general, one may require exponential number of classical bits to describe them. So an example, if you're already familiar with some of the quantum notation, this is how a quantum solution to quantum CSP could look like, which requires all these values AX to specify all across. So that's the difficulty, and that motivates a notion of complexity, which I'll be calling description complexity, which simply is how many bits I need to try and describe this solution to a quantum CSP. Given that, here's an interesting point, that this notion of description complexity and quantum CSP and so on, it comes from a computer science point of view, but it turns out that this notion is also natural and important in the real world setting, that is in particular in physics. So here's one example of that. So in physically interesting setting, there are some quantum CSPs which are particularly important, simply because they are how nature works. So here's an instance. So think of certain quantum variables or qubits sitting on a simple lattice on the vertices of the simple 2D lattice, and imagine all the quantum constraints acting over here, acting, for example, between these variables in a very nice and simple in a geometric fashion, in particular in the local fashion. Given this quantum CSP, it will have a solution, which will be a quantum state. And one can ask the following question. Is it possible for these solutions to be described easier than what I said earlier? So in general, quantum solutions could be very, very complex, but is it possible that for these quantum CSPs, which are relevant in physically interesting cases, that one can describe these solutions using small number of bits, polynomial number of bits? So before going into the details of this particular problem, we'll go back again to graphical models and talk about it a bit more. So I was talking about description complexity as being something that's innate to quantum, but that's not really true. It turns out that high description complexity also comes up in classical case, and that comes up because of randomness. So if you have a random variable on n bits, clearly you require in general 2 to the n-1 real numbers to specify that distribution. And graphical models, which we talked about in the previous part of the talk, they help a lot in reducing this complexity, in reducing this description complexity. Also, if you recall the graphical model that I showed you earlier, it factorizes in a certain nice fashion, depending on the graph structure. So to describe this whole thing, I just have to describe each part, which requires much less cost. And that, in fact, makes it interesting in statistics and computer science and so on. So in a very similar spirit, but in fact, coming from a different angle. Before that, I'll have to talk about one property. Sorry about this. I'll talk about one property of graphical models. And this property seems to be somewhat not so necessary for the classical case, but it will be very important in the quantum case. So let's talk about that. So if I have a graphical model, and let's say I divide the variables into two parts. Let's say I make a cut in the graph. That gives me 1, 2, and 3 to 6. There is a very simple property of these graphical models, which is that if I look at the amount of correlation, let's say in terms of mutual information between these variables and these variables, that only scales as the length of this cut, which basically captures the fact, the simplicity of these graphical models in the sense that all the information between these two parts, it carried through the edges of this graph. So the mutual information, not exactly equal to, but it's proportional to the length of the cut. Now this fact seems to be irrelevant for much of the study we do in the classical case, but as I mentioned, it will be important in the quantum case. So yeah, so going back to the point I was mentioning earlier, it turns out that very similar to graphical models as being a good model of a good and a simple model of describing natural systems. It is expected that even for the solutions to these quantum CSPs, which I showed on this nice and simple 2-dimensional lattice, it is expected that their description also looks akin to these graphical models. And this, in a technical way, it's called a tensor network. But the structure, as you can see here, very closely resembles that of graphical model. So the main question here is, how do we prove that this description indeed exists? Because if it exists, then it will say that these ground states or solutions to these simple CSPs are in fact very, very nice. And they can be described using small number of parameters, because one has to describe, again, just a small number of objects involved here. So before talking about what happens in 2D, I will quickly talk about even simpler kind of quantum CSP, which will be in one dimension. So in one dimension, imagine an even simpler setting, which, by the way, from the constraint satisfaction point of view, would look almost trivial, but it's still very interesting from the quantum point of view. So I have these qubits, which are variables as before, but now arranged in a nice and simple lattice. And the constraints are acting on the edges, as you can see here. Now, just like in the graphical model case, we can ask the following question. What is the mutual information between this part and this part of the solution to this quantum constraint? So it turns out that in the quantum case, this mutual information becomes very important. And it was shown in 2008 by Hastings in a celebrated result that the mutual information between these two parts behaves just like it does in the graphical model. That is, it scales as the size of the cut, which is, by the way, 1 here, so it scales as a constant. Now, the reason why this becomes very important in the quantum case is because mutual information is a measure of this thing known as entanglement, which in fact is the divide between classical and quantum. So let me talk about entanglement a bit, and then it will be clear why this small mutual information becomes very relevant for the quantum case. So entanglement is this mysterious, spooky correlation between quantum particles. And I guess the best way to really understand entanglement is to understand the lack of it. So imagine you have two particles and there is no entanglement between them. Then the way to think about them is that they're classical. And that's what kind of makes this interesting, because what it means is that if in a certain quantum CSP, if there is low entanglement everywhere, then one expects them to be close to being classical, and hence one expects them to have low description complexity. So that's the spirit of what happens in the one-dimensional quantum CSPs. So going back to this one-dimensional case, given these quantum CSPs, lack of entanglement, as shown by Hastings, allows you to prove that these quantum CSPs look like these graphical models or these tensor networks with this very simple structure, which precisely captures its properties. So here's where computer science point of view also enters the picture, enters the story. And that's because the best known results in one dimension for these one-dimensional quantum CSPs come from the computer science point of view, which was shown by these authors in 2013. And what they did is that they introduced the notion of polynomial approximation to ground state, which I will not have much time in detail, but I will come back to it very quickly again. And the idea is to approximate the ground state, which is the solution, in terms of a polynomial of the Hamiltonian, which, by the way, is a matrix. So, all right. Here's the question that one can ask for the two-dimensional case, which was the key focus of our discussion, which is it also true that just like a 2D graphical model, is it also true that the mutual information between certain region and its outside in the 2D case scales in a small manner? That is, it scales like the graphical models, that is, it scales as the area of this partition. Of course, you expect it to scale at least as the area, but much smaller than the volume, which can be much larger. So that is known as the area law conjecture in the two-dimension setting, which says that the entanglement, it doesn't have to be 0, but it should be small, like the area, instead of something large like the volume. And this conjecture turns out is one of the most important open questions in this line of research, and there's no proof of it for these quantum CSPs. And in fact, this polynomial approximation that I will touch upon quickly later, which was introduced by these computer science methods, it does not seem to work in this 2D setting. So in a work in progress that hopefully will be online soon, we are close to proving this conjecture for a very interesting class of quantum CSPs, which are known as the frustration-free quantum CSPs. The way to understand it from the computer science point of view is that frustration-free simply means all those quantum CSPs that are satisfiable, that have 0 unsatisfaction. So this result is an improvement over a prior work that appeared last year. So given this result, there's some technical backstory that comes with it. So I will spend 1 or 2 slides describing it. So as I mentioned, the previous works used polynomial approximations to the ground state, and their inspiration came from from computer science, which talks about best polynomial approximation to certain functions, in particular the AND function, uh, which is very well studied in complexity theory. So their inspiration came from Chebyshev polynomials, which are very good at approximating these objects at constant error. But it turns out that at smaller errors, there are much better polynomials known, again, which is a byproduct of complexity theory. So our technical contribution is achieving these polynomials which were known only in the classical context to these quantum contexts, to these quantum CSPs at these small errors, which was not known how to achieve in the previous work. But this is a technical point. But there is also a conceptual contribution, which is sort of one way to see it is as a contribution of computational point of view to the physics point of view, to the physics community. So the way one can think of these this small mutual information in these quantum CSPs, it comes from the way we think. We can think in the computer science point of view is well from the graphical models, but in the physics point of view, the thinking is slightly different. And this comes from the idea of correlations, where it is believed that in the solutions to these 2D CSPs, the correlation is only located at the boundary between the inside and the outside. Hence, the information should be small. But there's no proof of this point of view despite being around for a long time. What we are showing is that one has to replace this notion of correlation that comes from the physics perspective with a notion that comes from a computer science perspective, which is the optimal polynomial approximation, which I alluded to in the previous slide. And that seems to be replacing this perspective that was there in the physics, in the proof of this result. All right. So there are a series of questions to explore, which are very important in this particular line of research. So one question is to understand more general quantum CSPs. As I mentioned, our work applies to quantum CSPs which can be satisfied. But how about the quantum CSPs that don't have to be satisfied? They're very important in physics world. Of course, they're as important as satisfied quantum CSPs in the computer science world. So how do we understand that? And then beyond that, how do we go to more complicated systems? Let's say a 3-dimensional system, which would be even more relevant for the physical setting. Given that, the most important problem in this line of research is to get algorithms for these solutions to quantum CSPs. So getting those algorithms seems to be one very important task. So let me give you a bit of context on this. So having efficient description is great. Having low description complexity is great. But how do we find it? And that is something that is one of the major challenges. In fact, I would say the major challenge in this area. So that itself sits at the top of this line of research. And in fact, as I mentioned, that the way ground states are important for quantum computing, because they serve as a substrate for quantum computation, one expects that answer to this question will also have insights into the powers of quantum computation that can classical computers simulate quantum computers. All right. So that brings me to the end of this part of the talk. Let me quickly summarize it because it was quite long. An essential point of view here is that small description complexity is expected to hold in the 2-dimensional quantum CSPs and their solutions. And this question connects to the entanglement properties of ground states through this notion of mutual information. And we saw that the idea of polynomial approximation, which comes from computer science literature, it helps answer questions related to this, and it connects to the entanglement properties. So if there are any questions at this point, I can answer them, or else move to the third part of the talk. Okay, so I will now go to the third part, which will be the other spectrum of the study of quantum CSPs, which is how difficult are these quantum CSPs. So the first part of the talk was about how simple they are. So the second part was about how simple they are. Now we'll move on to how difficult they are to study. So so a very interesting question in CSPs is about the difficulty of approximating their solutions. As is well known, the Cook-Levin theorem, it says deciding whether a CSP is satisfiable or not is a difficult task. But what about the following easier task, which asks to decide whether a CSP is satisfiable or a good fraction of these constraints are unsatisfiable, which seems to be a more generous condition on these CSPs. It turns out that this problem is also difficult to solve, which is the content of the very well-known PCP theorem. And what it tells is that it is also difficult to approximate the solutions to a CSP, which by some means I know is satisfiable. So this talks about the hardness of approximation for these CSPs, that it's difficult to satisfy even a good fraction of these outside of these constraints. Now it turns out that this whole line of research is, of course, very relevant in theory of computing, but lately it has also found a lot of applications, in more practical settings, and for example, in cryptocurrencies and so on. All right, so in a very similar spirit to the Cook-Levin theorem and the study of NP completeness, it is also well known by now that deciding if a quantum CSP is satisfiable or not is also hard, but now it's the quantum version of NP hard, which is also known as QMA. One can ask us a very related question to the PCP theorem, which is, how about the easier question of deciding if a quantum CSP is satisfiable or it is unsatisfiable to a good fraction? Is this hard as well in the same sense as the quantum version of the Cook-Levin theorem is hard? Now, this problem turns out to be very, very difficult, and it has no resolution by now. And it turns out that if there are answers to this question, they would have implications in hardness of approximation of quantum CSPs, of course, but it also have applications in estimating energy in quantum many-body systems, which turns out to be a very, very important problem. So since this problem is very hard and there is no clear progress except lots of positive and negative results, Friedman and Hastings, they in 2014 asked a powerful conjecture, which was a necessary condition of the quantum PCP. What they asked is a question which kind of distills the first barrier that one faces towards understanding the quantum PCP. And this conjecture is about quantum circuits. So let me tell you about these objects. So these quantum circuits, very much like the classical circuits, they act on something that is very simple. Let's say a simple quantum state, just like a simple all zero strings or some input. And we apply gates for some time, or quantum gates for some time in a layer fashion. We say that a quantum circuit is constant depth if the number of times I apply the gate is not too long. That means if I apply the gate for a constant number of times. There are several nice properties of these quantum circuits. In the spirit of what I said earlier about the description of quantum states that come out of here, these quantum circuits are easy to describe. Well, simply because I have to just describe each of these gate to fully capture the output quantum state. Describing these gates along with this input is enough for me to describe what comes out of here. And because it's a constant depth, it's easy to do. What's another interesting property is that computation with these objects is very easy. So for example, if I want to compute how much is a quantum constraint not satisfied, I just have to use these constant depth quantum circuit as my ansatz, and that works very well. So the point is that if these constant depth quantum circuits, they're very simple, but if they're powerful enough that they can achieve very low unsatisfaction value for any quantum constraint, then it turns out that the quantum basic conjecture is false. Simply because one can use these two properties to give a classical way to prove the hardness of this problem of a given quantum constant satisfaction, whether it's satisfied or not. So Friedman and Hastings gave a conjecture which I will not try to expand at all, where they propose that this doesn't happen, that these constant depth quantum circuits, they're not strong enough. What they asked is it possible to have some quantum CSPs for which any such constant depth quantum state cannot achieve very low unsatisfaction or very low energy? That means any quantum state that achieves small value of unsatisfaction requires a large circuit depth, super constant circuit depth. There have been several efforts towards answering this question, but there's no clear there was no clear proof yet. But recently we came very close to answering this question, and we showed what is known as an almost version of the conjecture of Friedman and Hastings, where they showed that there are quantum CSPs for which any quantum state that can achieve not a constant but a little bit smaller than that energy requires a large circuit depth. Improving this to a constant would basically prove the conjecture of Friedman and Hastings. There are several intuitions that come here, which one of the intuition comes from the study of error correcting codes in the classical literature, where where one tries to prove that error correcting code words of error correcting codes are hard to prepare using small circuits. In fact, our result is quantum analog of these results, or in fact, even to the approximations to these code words, which capture the unsatisfaction value. Moreover, from the entanglement point of view, we show the presence of long range entanglement in these approximate code words, which is interesting on its own. Finally, this line of work, it kind of opens the door to several directions towards understanding quantum PCP. So let me tell you a few directions. One direction is, of course, well, the quantum PCP conjecture sits at the top. It's really one of the most important questions in quantum complexity theory, in the understanding of quantum CSPs. And NLTS conjecture is a way to achieve that, and we are somewhere here at this point, and we would like to understand this conjecture to get this to here. And another avenue is to understand a weakening of the quantum PCP conjecture itself via the almost quantum PCP, which, by the way, in the classical world would be fairly straightforward, but probably easier to think about. But in the quantum case, it's not easy at all. And can we prove a version of quantum PCP conjecture which is relaxed in the sense that one doesn't ask a constant unsatisfaction. At the same time, there's a lot to think about in terms of again what's happening in the quantum world lately. So as I mentioned, that low depth quantum circuits play a very important role in the NLTS conjecture, in the conjecture of Friedman and Hastings. And overall, low depth quantum circuits are also very well studied in other places, especially in the power of quantum computing, because one expects the quantum computers in the near future to be very small, to be these kind of circuits. So there are several results which try to study what can these quantum circuits really do, what kind of problems they can solve. And some famous examples of these are QAOA or VQE, where QAOA tries to solve problems in classical optimization, and VQE tries to solve more quantum-like problems, like let's say for quantum chemistry and so on. So our result has implications on this, and it says that low-depth circuits cannot solve certain quantum optimization problems or quantum version optimization problems. And in fact, our work falls into several line of research which tries to prove lower bounds on the power of low-depth quantum circuits. So again, this research on its own is an independent direction, but it also progress on it is expected to provide more clarity on the status of quantum PCP conjecture. So with that, I'm at the end of my talk. Let me tell you, as an outlook, we saw that the computational ideas have impact in fundamental questions in physics. I briefly touched upon strong convexity, which helped to understand the learning of the quantum Hamiltonian, learning of the Gibbs state. We also saw how polynomial approximations help understand the endowment structure of the solutions to quantum CSPs. And we also saw something in the other direction. So for example, we saw physical systems, they impact quantum complexity theory. So for example, we saw how quantum error correcting codes, they help understand quantum BCP conjecture by trying to give very canonical, very natural quantum CSPs, which can be a hard instance for quantum BCP conjecture. So this seems to be a new exchange of ideas between computational ideas and the physics world, but it kind of goes back a long time. So for example, I found it amusing to see the motivation for Chebyshev to come up with his famous polynomials. So Chebyshev seems to be studying and comparing different mechanisms of motion transfer, in particular in the steam engine, which was an engineering problem. And trying to solve that, he came up with these wonderful polynomials, which right now seems to be very useful in the study of quantum CSPs and of course in complexity theory. But again, these old connections, they have a new context, which is the quantum view on computation. And I'm excited to see where does this line of research go. So with that, thank you for your attention.
So we have a tiny bit of time for some questions, if there are any more.
I have one question. So I wanted to see the motivation for studying area law for, say, 2D. I mean, assuming that the area law conjecture is true, it seems that you still need 2 to the root n space to describe the the distribution. So I agree it improves from 2 to the n to 2 to the root n, but I don't still see why this would resolve the question. You still need exponential in n space.
I see. So that's a great question. Just one second, let me go back to that point in the talk. So the area law itself, it would say that the information is low, and that would, as you said, it would reduce the amount of information a little bit. But one expects that the proof of the area law, which would use these polynomial approximation tools, this would in fact show that these ground states can be described by these objects, which are tensor networks in 2D. And to describe these ground states, one needs small number of information on each side, which happens to be n bits of information if these are constant. So just like a graphical model, which, for example, would be requiring small number of information to describe completely, here as well one expects that one would require just to describe these matrices. In the tensor network language, these are matrices, and one just have to describe these matrices. So that is in fact linear in the number of particles. But did you think 2 to the power root n in a different point of view?
Cheyenne, did that answer your question, or? Yeah. Oh, I see. Good. Yeah. So Shyam is asking if you can talk more about sort of how this kind of work of studying quantum many-body systems and entanglement is relevant to sort of current efforts in quantum computing.
Right. As I mentioned here, oh yeah, here it is. So essentially, these solutions to these ground states, they are models of computation. So for example, one can use this. In fact, is a ground state of certain quantum CSP, and the way one computes the properties is just one keeps measuring in a certain way, and one gets to the answer. So ability to simulate these systems with a classical computer would put limitation on what the power of quantum computers. So for example, so the benchmark for a quantum computer to go beyond classical computer is not be able to be that it should not be simulated by a classical computer in an efficient manner. So in fact, being able to simulate these ground states using having an algorithm for these ground states would sort of restrict the kind of simple quantum computations one can think of in various settings, which are in fact, for example, the one over here. So just to give you an example, the tensor network language helps us understand the power of one-dimensional quantum computers. So if you have a quantum computer on a one-dimensional particles and it's not too deep, then one can simulate those using the tensor network ideas in linear time on a classical computer. So it shows that these quantum computers are not good examples of, are not the good candidates for simulation, although they're a very simple object and one would want them to be, but they're not. Is that a helpful answer?
Yeah, he said thank you. Okay, so let's with that let's end the talk, and we can take more questions. I mean, I guess over email or some other forum. Yeah, so thanks again.